Okay, let's move on to the next section of Chapter 4, which is going to involve going over the main types of reactions that occur in aqueous solution. So the first type of reaction that we're going to look at, and there are three in total, are what are called precipitation reactions. And these are chemical reactions where we have two soluble reactants, generally two soluble ionic compounds, that react together to form an insoluble solid product. And because the solid product is insoluble, it's not going to be dissolved in the aqueous solution, but instead it will be said to fall out of solution. So in this example here down in this beaker, we have the reaction of lead 2 nitrate, which is soluble, so it's in aqueous solution, and that reacts with potassium iodide, which is also soluble, and this forms aqueous potassium nitrate, soluble, and insoluble lead 2 iodide. And unlike the other reactants and products, you can see that this is a solid, and that's actually the orange solid that you see formed here when these two clear liquids are combined. The next type of reaction that we'll get into detail on are what are called acid-base neutralization reactions. And these are reactions where an acid reacts with a base, as the name implies, and the products of these reactions are generally water plus some ionic compound, and the ionic compound that's formed in any such reaction is referred to as a salt. So you might notice, for instance, here that one of the products of this reaction is sodium chloride, and in this case, sodium chloride, of course, is just sometimes called salt, but in chemistry, salt refers to any ionic compound that's formed as a result of an acid-base reaction. So sodium chloride is not the only possibility for a compound that can be classified as a salt. And finally, the last group of reactions that we're going to talk about are what are called oxidation reduction, or redox reactions for short. And these are processes in which one or more electrons are transferred between reactants. So the reactants can be elements, covalent compounds, ionic compounds, acids, pretty much anything. And the products are whatever you get when you transfer electrons from one reactant to another. Maybe the most obvious example of a redox reaction based on what we've looked at so far would be forming a compound like sodium chloride from sodium metal and chlorine gas, where you're starting with neutral sodium atoms and neutral chlorine atoms and ending up with sodium cations and chloride anions because the sodium atoms transfer electrons to the chlorine atoms, turning them into chloride ions. Now, the scope of oxidation reduction reactions is a lot larger than that, and without getting into more details, which is something we're going to do at the end of this chapter, it's not necessarily that easy to identify if something is a redox reaction. So we'll talk later on about how you can actually determine if a redox reaction is occurring based on certain parameters. As we've seen on the previous slides, you can represent a chemical reaction in aqueous solution, so any of the previous three examples, with, of course, a balanced chemical equation. And when you write out the full chemical formula for all the reactants and products, and of course balance everything with the correct stoichiometric coefficients, you're going to end up with what we call a molecular equation. And this means that all the substances in the chemical equation, both reactants and products, are written with their complete chemical formulas, just like if they were made up of molecules. Now, of course, with ionic compounds, especially ones that are dissolved in aqueous solution, we know that they're not made of molecules, they're going to be made up of discrete cations and anions. But when we write out the whole formula, it doesn't necessarily give you a great way to distinguish between whether something's made up of ions or molecules, other than to kind of know what formulas for ionic compounds look like based on what we talked about in Chapter 2. Now, as it turns out, molecular equations often provide extraneous information compared to what's actually going on in a chemical reaction in an aqueous solution. So, as an example, we can go back to the precipitation reaction from a few slides ago where we formed a solid, or as it's known, precipitate of lead 2 iodide from the combination of lead 2 nitrate and potassium iodide solutions. Now, what we can do is, as shown on the previous slide, we can identify all the compounds that are strong electrolytes, and that depends on which compounds are both ionic and present in aqueous solution because they are capable of dissolving. And both reactants and one of the products, in this case potassium nitrate, all fulfill those requirements. And as we saw earlier, lead 2 iodide, while it's ionic, it's made up of lead ions and iodide ions, is not soluble because it forms a solid in this reaction. So that is not a strong electrolyte, again, because it's not capable of dissolving in the first place. So we won't show this as dissociated because it's not dissociated, but everything else here, based on what I've told you so far, being a strong electrolyte should be dissociated when it's in aqueous solution. And so we can represent this equation, really we can expand this equation so that all the reactants and products that happen to be strong electrolytes are going to be shown as separate dissociated ions, because really that's a more accurate picture of what's going on. So in the case of PbNO3 we know NO3 is nitrate. Each of those is -1. So if we have 2 of those for every 1 lead, that means that the ions we dissociate into are going to be nitrate ions and lead 2+ ions, because you need 2+ to cancel the 2 -1 charges from your nitrates. And this 2 here means, of course, we're going to have 2 nitrate ions when this is dissociated. We can do the same thing with potassium iodide. This formula contains 1 potassium plus 1 cation, 1 iodide minus 1 anion, and there's a 2 in front, so we need to multiply both of those numbers by 2 when we show this as dissociated in the balanced equation. So we have 2 potassium ions and 2 iodide ions in aqueous solution. Same thing here for potassium nitrate, which has nitrate and potassium ions, and there's a 2 in front, so we need to double both of those amounts, 2 potassium ions, 2 nitrate ions, and again, for the previously stated reasons, lead 2 iodide is a solid that does not dissolve and is not going to be shown as dissociated because it is not dissociated. Now, if we look at this equation, you might see that there are 2 ions, potassium ions and nitrate ions, that show up in the exact same form on both sides of this equation. And kind of like an algebraic equation, if you're simplifying one of those, that means that really nothing is going on with the potassium ions and the nitrate ions. They're still present. When we had our lead nitrate solution, we have our nitrate ions there, and when we had our potassium iodide solution, that contained potassium ions, of course. And both of those things are still going to be present after the reaction takes place, but the potassium ions and the nitrate ions didn't change form. They were dissociated in aqueous solution before the reaction took place, and then after the reaction took place, they were still dissolved in aqueous solution. And so these are what are referred to as spectator ions, because they don't undergo any change during the reaction. And so they're said to spectate the actual reaction. They're basically watching everything else happen. So even though those ions are present in the reactants and the products, the only sort of actual chemical change that happens here is the combination of the dissociated lead ions and dissociated iodide ions to form solid lead 2 iodide. So those ions change form because initially they were dissolved in solution, but now they've combined together to form a solid. But the potassium ions and nitrate ions are spectator ions. And so like an algebraic equation, if something shows up on both sides, we can essentially cancel it out. So if we remove the potassium and the nitrate ions from both the reactant and product side, since they didn't change, we end up with what's called a net ionic equation. And this shows only the ions or other substances in a reaction that are actually undergoing some sort of chemical change. Now, taking a balanced molecular equation and turning it into a net ionic equation is, of course, kind of a multi-step process because you need to go through all the steps that I just showed you. And for that reason, it can be kind of confusing for some people. But if you can show me how to balance a net ionic equation and show me that you can consistently do that with very high accuracy, that shows me all at once that you have mastered a whole bunch of concepts. So not only the concepts that I just showed you in terms of actually deriving a net ionic equation, but also that you understand how electrolytes, that you understand how chemical formulas are composed of ions and how to come up with correct formulas for ionic equations and so on. And as we'll see in a later section, this will also show that you understand how to apply the solubility rules, which are the rules that govern whether an ionic compound should be soluble or not. So there's actually a lot of stuff tied up in being able to derive a net ionic equation. And so for that reason, it probably wouldn't be a bad idea to find all the questions in Chapter 4, both in the regular portion of the text and at the end of the chapter, and try to turn all of the molecular equations in those problems into net ionic equations. The better you are at this, the better you're going to be at a whole lot of different things that show up in this class.